In this video, we're going to be looking at the double content of topic 4C, the alkanes, and this is part of the IGCSE chemistry course from Edexcel. So we're going to be looking at the general formula for the alkanes. We'll be discussing why we class them as saturated hydrocarbons, being able to draw the structural and displayed formula for the first 5, and be able to name these, and then looking at the reactions of alkanes with halogens in the presence of ultraviolet radiation, and how we can write out the equations to show how this process happens. So the alkanes are the most simple homologous series of hydrocarbons. Now remember, a homologous series means that they are going to have trends in their physical properties, they're going to share similar chemical properties, and they will have the same general formula. So a homologous series is just another word for a family of compounds. And of course they are all hydrocarbons because they contain only hydrogen and carbon. And we call these saturated hydrocarbons because they contain only single carbon-to-carbon bonds. We do not have any double bonds, so we call these saturated hydrocarbons. Now the general formula for the alkanes is CnH2n plus 2, meaning we have a specific number of carbons, and to work out the number of hydrogens, we multiply it by 2 and we add 2. So for example, if our carbons was 20, to work out my hydrogens, I would do 20 times 2 and then add 2, which would give me 42, meaning my formula would be C20H42. So you'll be able to work out the formula for any alkane of any number of carbons using that general formula. So it's extremely important that you remember this. It is a very common exam question for 1 mark asking for the general formula. Now with regards to the formula and structures and names, you're only required to know by heart the first 5. Now you may get asked about alkanes with 6, 7 or 8 or even all the way up to 10 carbons. However, you will not be expected to know the structures of those. You will be able to work them out, of course, using logic. However, you would be given all of that information in an exam. So don't worry about that. You're only expected to know the first 5. So let's have a look at these. So the first 5, the first one that we start off with is methane. Now for the alkanes, all of them are named in very much the same way, and we want to think of them as a family. So we're going to break down the names into 2 parts. We have meth and we have ane. So I want you to think of the ane as their family name or their surname. So every single member of the alkanes will end in ane. That is their family name. And the bit at the start, in this case meth, tells us how many carbons it has. And if it has meth, it means 1 carbon. And we will see as we go through that that part will change, and that tells us how many carbons are in each of our alkanes. So we're going to go from the name and we're going to go to the displayed formula, because that's actually the easiest to work out, and then you work your way back to the molecular or the structural formula. So you have your 1 carbon, and it should be completely saturated, meaning it has only single bonds, and we have then 4 hydrogens surrounding the carbon, and that is the displayed formula for methane. For the structural formula, we just take that and we condense it. So the displayed formula will show all the bonds. The structural formula shows the structure but in a shortened version. So we take it in small chunks. So the structural here is CH4, telling us I have a carbon surrounded by 4 hydrogens. And for the molecular, that is just simply the number of carbons and the number of hydrogens. So methane is the only one where its structural formula is the same as its molecular formula. Nice and simple. So let's move on to the second alkane, and that is known as ethane. Now again, they end in ane because that's the family name, and eth this time means 2 carbons. So if we go to our displayed, we have 2 carbons in a row connected by 1 single covalent bond. Remember, these are saturated, so no double bonds here. And then all you do, you surround all the carbons with hydrogens, making sure that every single carbon has 4 bonds. And you get a structure that looks like that. Now we want to then make the structural formula. We condense it into smaller chunks and we take each carbon as a chunk. So we take CH3 and then the next chunk is CH3. That's our structural formula. So it's showing the same thing as the displayed formula, but just not showing the physical bonds. And the molecular is simply counting. So we have C2H6. Again, we can see that that's fitting in with our CnH2n+2 general formula that we've already discussed. The third one is prop-N, prop meaning 3. So I have my 3 carbons in a row, all single bonds and surrounded all by hydrogens, making sure that every single carbon has 4 bonds. My structural formula, as we know, takes that into a smaller section, and we have CH3, CH2, CH3. So we're just breaking it down into these small chunks like that. And our molecular, again, counting how many carbons and how many hydrogens, we have C3H8. So that's the first 3. You're required to know the first 5, so we have 2 more. The next one is butane, and but meaning 4 carbons in a row. And again, we surround them all with hydrogens. There are no double bonds here, so every single carbon is going to have hydrogens attached with 4 bonds. Our structural formula takes them into small chunks, so we have a CH3, CH2, a CH2, and a CH3. You'll notice that each time we're extending the chain and moving up another carbon, we are adding a CH2 into the centre of our structural and our displayed formula. That's what the homologous series, so each member differs by CH2. And for the molecular formula, we have 4 carbons and 10 hydrogens. And the last one that we have to know is pentane. So pent meaning 5, similar to a pentagon. And the ANE, of course, tells us that it is part of the alkane family. So we have 1, 2, 3, 4, 5. And then we surround all of the carbons again with all hydrogens, making sure everything is a single bond and every single carbon has 4 bonds. I then break it down for my structural, so I start with CH3 and then I'm going to add in that extra CH2. So I should have 3 CH2s and then finishing with the CH3 at either end. And again, lastly, the molecular formula is C5H12 in order to count them. So you can see that that's the information that you can find in the textbook as well. So these are must know, and you should be able to replicate these in an exam, whether it be the name, the molecular formula, the structural, or the displayed. Please be aware in a question, make sure that you read what it is asking you for. If it asks for a displayed and you only give a structural, you will lose marks. So be very, very aware of the different types of formula that we can draw. And if you're not sure and you want some more practice, you can go back and have a look at the video from topic 4A, where it goes into a bit more detail about them. And you can find some extra questions in the textbook. Now, in topic 4A, we mentioned isomers, and alkanes can have isomers. So remember, this is where we have the same molecular formula, but we have a different structure. All of the alkanes that we've just looked at are all straight chain, meaning all of their carbons are in a row. Now, what we can do is we can actually take some of the carbons out of the chain and put them as a branch or a side chain and form an isomer. So an example would be C5H12. Now we just met C5H12 with 5 carbons in a row, where it looks like this, and we called this molecule pentane. Now that is one isomer of C5H12. There are actually 3 isomers of C5H12. So what we can do is we can take our chain of 5, we can remove one of them, and we can put that as a side chain. So we're going to have 4 carbons this time, and I'm going to put my chain here on the second carbon. Remember, it can't go at the ends, it has to go in the center. And then all I would do is fill all of my hydrogens around again, making sure that each carbon has 4 bonds. And if you count them, we can see that we have 5 carbons and 12 hydrogens again. And this is known as 2-methyl butane. Now we can again take one of the carbons from that chain, and so that I now only have 3 carbons in my center chain. I still keep that side chain on the second carbon, but now I add a side chain at the top as well. And again, once I put in all my hydrogens, hopefully you can see that there are 4 carbons with the hydrogens, and each of them has 3. So that is again C5H12, and this one is known as 2,2-dimethyl propane. Now, in an exam, you may be asked to name them, but that's a less likely question. The majority of questions on isomers that you will be asked are to draw possible isomers. Now, you might want to practice this, and you can find some more examples in topic 4A, or check back on the channel for the video on drawing isomers, or ask your teacher for some help. Now, we also have trends in the physical properties because they are a homologous series, and what we see is the first 4 alkanes are gases at room temperature, and these are actually the refinery gases that we met in fractional distillation. So methane, ethane, propane and butane are all gases, and you've probably come across some of these in your everyday life where you've maybe heard propane or butane gas for things like barbecues. For carbons 5 to 17, when we have an alkane, these are all liquids. So pentane, hexane, heptane and octane would all be liquids, and actually octane, which has 8 carbons, is what we find in petrol or gasoline. Again, we get that from our fractional distillation. Anything above 17 carbons is then going to be a solid. So that's the trend that we see, that as we increase the number of carbons, we're going to get an increase in our our melting point. And this increase in the melting point is due to increased intermolecular forces of attraction between the molecules. Now, you don't need to know what these forces of attraction are, that is A level, but you simply need to know that they exist, and as the molecule gets bigger, they become stronger. And because they become stronger, they require large amounts of energy to be broken, meaning we have an increase in the boiling points. And that's the trend that we see in this homologous series. They all have the same sort of bonding and functional groups, so the fact that we have carbons singly bonded to each other and carbons singly bonded to hydrogens, meaning they react in very similar ways. Now, actually, the alkanes are not entirely reactive. They are fairly inert, and this is because the carbon-to-carbon bonds and the carbon-to-hydrogen bonds are very strong, meaning they take a lot of energy in order to break to then allow the reaction of the molecule to happen. So because this doesn't happen particularly easily, they are thought to be inert molecules. But there are some key reactions that can happen, and you are required to know 2 of them. Now, the first we've looked at already when we looked again back in topics 4A and 4B when we're talking about combustion. So the complete combustion, meaning we have lots of oxygen or a plentiful supply of oxygen, when we burn an alkane, is going to form carbon dioxide and water. So for example, if we have methane, which is CH4, and its state symbol, of course, is a gas, reacting with oxygen as a gas, we're going to get carbon dioxide and water. Now, as with any chemical equation at IGCSE, you are expected to balance it. So we would balance out first the carbons. I have 1 and 1, which is perfect. The hydrogens, I have 4 on the left and only 2 on the right. So I put a 2 in front of the water to then give me 4. And my oxygens, well, on the right hand side I have 2 from the carbon dioxide and 2 from the water, which is 4. I then divide that by 2 to give me the oxygens. So my coefficient in front of there is 2. Again, we can have the same thing for pentane. So pentane is C5H12. It is a liquid. We have oxygen. And we still make carbon dioxide and water. That does not change. What will change, however, is how much of it we make. So if we have 5 carbons on the left, we need 5 carbons on the right. I have 12 hydrogens on the left. I only have 2 on the right, so I need to put a coefficient of 6 in front of my water. I then add up my oxygens. Well, I have 10 coming from the carbon dioxide and 6 coming from the water, which is 16. If I divide that by 2, I get a coefficient of 8. Please make sure that you practice writing out the combustion reactions and balancing them. Again, whenever you're doing a balancing of a combustion of a hydrocarbon, you should always start with the carbons first, then the hydrogens, and then you add the oxygens and the products and divide it by 2 to give you the coefficient in front of the oxygen. And remember, you can have fractions, you can have halves. If you're not sure, there are some practice questions that you can find online or in the textbook, or again, of course, ask your teacher, or feel free to leave a question below in the comments and I'll get back to you. We can also have incomplete combustion. So this is when we have a lack of oxygen or not enough oxygen, and this can form carbon monoxide or even carbon in the form of soot. And of course, we still make the water. So if we have the incomplete combustion of ethane, so we have C2H6, which is a gas, still reacting with oxygen, but because it's incomplete combustion, this time we're going to make carbon monoxide, and we still make the water. And then when we balance this, we can see that we end up with the following coefficients. Or you may also have a coefficient of 1, 2.5, 2, and 3. They would be perfectly acceptable, just as long as your ratios are the same. Or we can also have the same alkane reacting with oxygen, but there's not enough oxygen to even make the carbon monoxide, and this time we simply just have carbon being formed. And all of the oxygen is only reacting with the hydrogen. And if that is the case, again, we get the following coefficients. So you can see that each time we've done a complete combustion to an incomplete combustion, we are reducing the amount of oxygen that we're using. That's showing us that we don't have enough oxygen for this reaction to fully happen. Now, the second reaction that you have to know for the alkanes are substitution reactions. So despite the alkanes being quite inert, they can actually react with halogens in the presence of ultraviolet or UV radiation. This is a very key thing to know because this is the condition that we need in order for the reaction to occur, and it is a very common exam question. If you do not have UV light or sunlight, this reaction will not take place. So the purpose of the UV light is used to break the bonds between the halogen molecules. And you'll learn more about the process that this undergoes and how it works if you do A-level chemistry. For IGCSE, you simply have to know that you have alkanes reacting with halogens in the presence of UV light, and you have to note the products. So what actually happens here is a hydrogen atom in the alkane is now replaced by a halogen atom. And this is known as a substitution reaction because we are swapping out one atom for a different one. Just the same as if it was in a football match and you had one player coming off of the pitch and another player going on, we call that a substitution. It's the same logic here. We're substituting one atom in the alkane for a new atom, in this case, a halogen. Now, the halogens that can be used can be any of them, but the most common ones are either chlorine or bromine. These will be the two that you will get asked about in exams. In theory, you can use fluorine, iodine, or astatine, but they are very rarely asked about. So if we have a mixture of methane and bromine gas, this mixture is orange, and that is due to the bromine. Bromine has this orangey colour when it is as a gas. Methane is colourless, so it does not contribute. All of the orange comes from the bromine. When you have this mixture and you put it in a gas jar and expose it to sunlight, what actually happens is it loses its colour, and we get a mixture of bromomethane and hydrogen bromide being formed. So what we want to see is what this actually looks like. So if we have methane, which we know is CH4, like that, and we react it with bromine. Now remember, bromine is diatomic, so it is Br2. This is going to form this new compound, bromomethane. And what actually happens is this bond here between the halogens breaks, and one of the bromines takes the place of one of the hydrogens. And when that hydrogen is removed, it then comes and reacts with this bromine, forming hydrogen bromide. We can then look at the new compounds that are formed. So we have our carbon with the 3 hydrogens that it started with. That's not changed, but this 4th hydrogen has now become a bromine. And we also have the hydrogen that was lost bonding with the bromine that is left. So this is methane plus bromine, giving us bromomethane. So we call it bromomethane because we have methane as the main structure, but we've added in a bromine and we shorten that to bromo. And we also form hydrogen bromide. And of course, we could write out the formulas where we have CH4 plus Br2, both of which in this case are gases, and we form bromomethane, which is CH3Br as a gas, and hydrogen bromide is HBr, and it is also a gas. So all of this is done as gases. So a substitution reaction is the halogen molecule breaking down into 2 atoms, and one of the halogen atoms replacing a hydrogen on the alkane, and the hydrogen then reacting and bonding with the halogen atom that is left. This can happen with any alkane, and it could happen to any of the hydrogens on the alkane. Now, we call this mono substitution. Mono meaning we have one hydrogen being replaced. The problem that arises is once we start to get to larger molecules, such as propane, which has got 3 carbons, the substitution reaction can happen in different places on different carbons, which means that we can actually have different isomers. So if we have our propane, which is C3H8, what can happen is we could replace this hydrogen here with a bromine, and we would call this 1-bromopropane. And we call it this because the bromine is on carbon number 1. However, the bromine could substitute onto carbon number 2, and we would get a molecule then that looked slightly different, where the bromine is now on the 2nd carbon, and we would call this one 2 bromopropane. Now, 3-bromopropane does not exist because if I was to move the bromine to the carbon on the left and continue to move it down the chain, we would start the numbering from the other side. So we can only get 1-bromopropane or 2-bromopropane. These are both isomers because they have the same molecular formula, but they have different structures. So they are both C3H1234567 Br. But because we have these different structures, then they call them isomers. So we just have to be aware that for the larger molecules, we can get isomers being formed. But for methane and ethane, we only make one possible product. And we call these products bromoalkanes. Now, the same thing can happen with chlorine. The only difference is rather than writing a Br, you would write a Cl. And these would be known as 1-chloropropane or 2-chloropropane. Everything else is the same. The only thing that actually changes is the atoms that are used. So let's finish off by looking at some past paper questions. So alkanes are saturated hydrocarbons that can be obtained from crude oil, and we know that this is from fractional distillation. The general formula of the homologous series of alkanes is CnH2n plus 2. For 1 mark, what is the meaning of saturated? So why do we call alkanes saturated molecules? And it is because all the carbon to carbon bonds are single bonds, or you could even say single covalent bonds, and that would get you the mark. You could phrase it the other way, where you say that there are no double bonds between the carbons. So you can phrase it as what is there or what is not there. Either one would be accepted for 1 mark. And then part 2, the gold standard question for an organic paper: what is a hydrocarbon? It is always worth 2 marks, and you should have this drilled into your head by now. A hydrocarbon is a compound formed from hydrogen and carbon, and then that key word, only. That word of only gets you the 2nd mark. So always make sure that you do include that. So pentane is an alkane with 5 carbons in its molecule. What is its molecular formula? Well, this is where we could use that general formula that they told us. Pentane is one of the ones that you should know, but you can always double check. So Cn, well, if n equals 5, 2 times 5 plus 2 is 12. So I should have C5H12, meaning that my answer is C for 1 mark. Now octane, and you can see you're not expected to know that, so they do give you C8H18, is an alkane that is present in petrol. When octane burns completely, it forms carbon dioxide and water. Write a chemical equation for the complete combustion of octane. We have C8H18. We react it with O2. Remember, oxygen is diatomic, so it's always O2. And we know that we form carbon dioxide and water, as the question told us this. That would get you 1 mark. Your 2nd mark comes from the balancing. So if we have 8 carbons on the left-hand side, we need 8 on the right, so we put a coefficient of 8 in front of the CO2. I have 18 hydrogens, but I only have 2 on this side. Remember, I can't just change the formula, I have to put a coefficient, and if I put a coefficient of 9, 9 times 2 is 18. So now my hydrogens are balanced. That leaves us with the oxygens, so I add them together, and I get 8 times 2 is 16, plus 9 is 25. I can then divide that by 2 to give me my number of oxygens, and we get an answer of 12.5. Remember, you can have halves in complete combustion reactions for the oxygen, but you could have multiple. So you could have 2, 25, 16 and 18. As long as your ratios are correct, you would get the second mark here. In part 2, give the name of the toxic gas that may be produced by the incomplete combustion. Well, that's one that we know, we've covered multiple times. That is carbon monoxide for 1 mark. Now this question is looking at the substitution reaction. So when methane reacts with bromine, one of the products is hydrogen bromide. As I mentioned, state the condition. It's always a key question. We need UV light. They will also accept sunlight as an answer. Okay, it's nothing to do with the temperature, so don't talk about that it needs to be hot. It's not to do with the heat, it's to do with the UV light itself. And then the organic product that is formed, well, when the methane is substituted with 1 bromine, we are going to form bromomethane. So to name the organic product, you take the name of the alkane and you put the word bromo in front of it. And if it is something that is a larger alkane, then you specify which carbon it's on. And then lastly, for 2 marks, write a chemical equation. Well, the chemical formula for methane is CH4. We are going to add it to the bromine, which is Br2. The bromomethane is when we've substituted out one of the hydrogens. So we have CH3, and that 4th hydrogen is substituted with a Br. And then the last thing is hydrogen bromide, which is 1 hydrogen and 1 bromine. We don't need any state symbols here. You don't get any marks for that. You just get 2 marks. The first mark comes from your CH3Br, and then your second mark for everything else, and they're all in a 1-to-1 ratio, so no balancing is required. So there you can check the answers to the first set of past paper questions if you were trying them on your own. And then the last questions where you can see the information about the substitution reactions. Now that's everything for topic 4C, the alkanes, and this is for the double content. If you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.